Okay, so carrying on from the resistance stuff we were doing before. Okay, we'll kind of carry on with this resistance maths. Now, the rules that we've learned so far about resistance was resistance in series is where you just add up all the individual resistances, however many there are. And resistance in parallel was where you add up all the reciprocals of the resistances. That's like putting them under one, however many there are, yeah, and then divide that into one. Okay, so it's the reciprocal of the sum of the reciprocals. Okay, so that's the two different rules, and all you need to do is plug the numbers in to work out the total resistances. Now, and I gave you a hint. I told you how to work out when you're looking at a circuit. How do you know if the circuit you're looking at is series or parallel? So in a series circuit, there will only ever be one single path for the current to flow from one end of the supply to the other. Whereas in a parallel circuit, there will be more than one path. Now that means you'll see a node. Yeah, you'll see somewhere where the path splits in two. So you see wee nodes in there, so that tells you it's a parallel circuit. That tells you the resistances are in parallel, and therefore you must use this rule to work out the total resistance. And this one tells you the resistance is in series, and therefore you must use this one to work out the total resistance. So two different types of circuit, two different equations. And we've already talked about the merits of these two circuits, like if these resistances were actually bulbs in series, if one bulb blew, the other one wouldn't work either. Whereas in here, if both of these resistances were actually bulbs, if one bulb blew, the other one would keep working. So parallel is essentially a better way to wire things, really, because it means that the individual components aren't dependent on each other. They don't affect each other electrically. Right, okay. Now, it's possible, and this is the focus of today's lesson, it's possible to have a circuit that has series and parallel in it, right? So you could have, I'll show you a couple of different kind of topologies. You could have a circuit like that, and then the branch occurs after something. And you see a circuit shaped like that. So what you can see here is any current that's being drawn out of that supply goes through that resistor. All of the circuit current goes through that resistor. And then it splits at that node, and you've got a wee parallel network within the circuit. Yeah, so some of the current goes that way, and some of the current goes that way. And how much of the current goes one way or the other depends on how big the resistances are. So there's one way where you could have a series, and there's an infinite number of ways. I'm just going to kind of draw a couple of different versions of it, right? So it could look like that, or it could look like this, where you've got the resistances in parallel, and it doesn't ever have to be two. I know I get lazy and only draw two, right? But it could be as many resistances in parallel as you want. So there's our wee nodes, that tells us that's the parallel bit, and then you could have a wee series bit there. So that bit's in parallel, and then that parallel network is in series with that, and that's the same, that's in parallel, and that parallel network is in series with that. So remember, we use these equations to work out what we call equivalent resistances. So we're taking the real circuit and we're working out what it must be equivalent to, and that's what we could do here. We could work out the equivalent resistance of that parallel network, and that would just appear in series. So it would be this resistor plus the equivalent parallel one would give us the total resistance, and then the same over here. Other different kind of styles of the question you could have two resistances in parallel in series with another parallel network. Probably more common than you would think. And again, you could lay these out anyway. You need to try to recognise how the circuit's laid out by looking for the nodes and trying to work out what's in series. So, is there any other ones that I could think of? Yeah, you could have this one. Go to get lazy again and just do 2. Oi oi. What's happening in here? So in there, you've got these two are in series with each other, and then whatever the result of that series resistance is in parallel with that one. Yeah, so you need to watch out. There is another one, in fact, that I just thought of there, because you could have a parallel within a parallel. So move that up out of the way. So you could have your supply, and you could have that. Yeah, so they could do this. Don't get confused. It wouldn't matter, even if you got confused. You know, even if you thought, right, these two, but let's work these two out first, and then take that equivalent resistance and put that in parallel with that one. All 3 of them are in parallel with each other. That's just 3 resistances in parallel. That's just the same as that one, but it's just the way it's drawn is kind of funny. Right, so these are all the different types of things you want to work out or watch out for. So, you know, how would this resolve if that was R1, R2, and R3? How could you resolve that? Right, so let me just kind of talk through the kind of theory of it with no numbers. Right, so there's no, I'm not going to do any maths just now. Oh, I'm not going to do any maths just now in this example. I'm just going to do some, what's happening here? Oh, for goodness sake. Right, so I'm just going to do some like a wee think through essentially. Let's move them into a better order. Make them a wee bit smaller. So you can see I've given all the resistance names, and all I'm going to do is talk through how we would work out what the total resistance was. Right, so in here, in this instance, you would have to, before you could work out the series resistance, you'd have to know what this was worth. So you'd have to do the parallel resistance and then you'd have to put that into the series resistance. Look, RP. Yeah, I'm tracking what I write here. And this is the same, just in reverse. You know, the circuit's in reverse, but electrically it's exactly the same. You'd have to work out the parallel resistance first. That's 1 over R1 plus 1 over R2 plus 1 over R3, all divided into 1. And then you'd have to put that into that series bit. So that would be R4 plus RP. This one, they're all in parallel. I just do that kind of funny, so it would only be a bit, if you kind of fell for what they were doing, then it would be 1 over R1 plus 1 over R2. You know, if you worked that bit out first, and then it would, if you did the next bit, then that would just be the second RP would be, we'll give them names, RP1 and RP2, so that would be 1 over, stick with the program, 1 over RP1 plus 1 over R3 divided into 1. Now would you do this one? So you'd have to do your first parallel, RP1 is 1 over R1 plus 1 over R2. Your second parallel, and that gives you, so that first one gives you an equivalent resistance here. Incidentally, you should probably be drawing these, right? So that circuit after this point here, this circuit would become R1, and then you're replacing that parallel branch with an equivalent resistance, and you can see they're just in series with each other. Then you would do that, and then that's the same deal over here. after you do that first calculation, you would redraw the circuit to look like that. I've just turned those three resistors into one equivalent resistor that's in series with R4. And the same deal here. I've just turned that one into a single resistance that's in parallel with R3. So that's RP1 and that's R3. As you can see, that RP2 is in the final one. So then over here, after you do that first calculation, you've got a circuit that looks like that. I've just turned R1 and R2 into RP1, but I've still got this parallel branch here of R3 and R4. That I need to resolve, and that's what I'm about to do. So 1 over R3 plus 1 over R4 all under 1 resolves that down to 1. Just put it in here. So that's me got RP1, and now I've got RP2. So then the last calculation, that one would be RS equals RP1 plus RP2. It's important that you would draw those circuits. You know, you would sketch that circuit out first and do the maths for it, and then sketch the new circuit that you've got, just to keep it in your head. Now, I don't want you to lose sight of the context here. We're learning this skill about how resistances mess about with each other for two reasons. One, we'll be able to do calculations on circuits that have got all sorts of components in them, like thermistors or bulbs or whatever, if we know the resistances of them. And we are going to go on and use this as a basis to be able to then work out things like voltage and current in the circuit as well. Whether it's bulbs or thermistors or light dependent resistors, it doesn't matter the components, we're just using resistors as placeholders here. Don't lose sight of the bigger picture. We need to be able to work out how resistances are messing about with each other, and that's why it would be important to kind of keep track of what you think the circuit looks like at this point, right? So then this last one, in the last one, we're going to work out that series resistance. RS is R1 plus R2, so our circuit then becomes a simple parallel with two resistors in it. Confusingly, one of those resistors is going to be called RS, and that's R3, and then the last thing you would do would be RP. So that's 1 over RS plus 1 over R3 all under 1. So that's the way we tackle these different types, these different shapes. So make sure you copy that out and pay attention to it and understand it. If you don't understand any of that stuff, then ask me, okay? What I'm going to do now is set a bunch of questions where you have to work out the total resistance. And what I'd be expecting is that you go through this process, and in every instance, I'll give you like 10 questions or whatever, and in every instance at the end, you arrive at a circuit that looks like, this puts a new page in for me. It's refusing to put a page out. Oh, here we go. So at every instance, I'm expecting the last circuit to look like that. A power supply with one resistor. You're working out the total equivalent resistance of this thing. Don't worry if your circuit looks like that. Still a power supply with one single resistor. Alright. Okay, let me put some questions together. Give me a second. Right, okay, so there's 8 questions for you to work out the total equivalent resistance. So this one's very much just like the examples I talked about, where you work out the parallel bit and then add it to the series bit. In here, watch out for the parallel bit. When you're looking for nodes, they don't always have to be in the centre of the line, like the node's off centre, but there's still a node top and bottom of that, so that bit's parallel. Oh, that bit's series. Same over here, there's a series with a parallel branch. Again, there's a parallel bit in the middle of two things that are in series with it. There's two parallels with a series at the end. There's a series within a parallel. And within a series, yeah, so there's a series into a parallel. There's a series within a parallel that's got another series inside it, and then another series. Right, so you're just working out the total equivalent resistance. I'd expect you to draw this circuit at every stage, so that you're really breaking down what's happening with this circuit. So the more calculations you have to do, the more times you'll have to draw an equivalent circuit. Okay. Watch out for the numbers. Remember, we should be rounding to the correct number of significant figures. So in here, or those three numbers all have two significant figures. So your final answer for the equivalent resistance should be rounded to two significant figures. Don't round anything in the middle of the calculation. Keep the numbers as long as you can. Only round your very final number. Again, they've all got two significant figures. Watch out, because in one of these questions, or two of these questions, I've messed about with either the units, the magnitude of the units. Remember, if you see a K, that means 1,000. So that number there is 62,000. That number there, 2K9, that's 2.9 thousand, so 2,900. If you see no units, that just means ohms. So just the same as the ohm symbol, that's 2.9 ohms. That's 2.0 ohms. You need to ask yourself how many significant figures has that got. You need to be careful with that one. Capital M means million, so that's 4 million, 2.9 million ohms, with a 20 ohms in there and so on, so watch out for that, okay? Right, all the best. Bye.